Chapter 18 today. This is a chapter on essentially the same things, potential, kinetic energy, work done, but as applied to rigid bodies as opposed to particles. Okay, so what happens essentially is the formulas get a little bit more complicated, uh, but the ideas are the same. So let me review a few things before we get started with problems. Okay, so central to evaluating velocities and positions using this method is to find the kinetic energy. Now, for the kinetic energy for a particle is half mv square, right? Turns out for pure translation, that's true. So if the body is translating but not rotating, then you can apply the same formula to find the kinetic energy. It's half mvg square. Okay. The second case is rotation about fixed axis. So this is sort of mirroring the things we talked about in 2 chapters back. So on rigid body kinetics, right? There was rotation about fixed axis. So an object, it's rotating about O. You can write the kinetic energy two ways. One is to say that the total energy is half mvg square. This is the center of mass plus half ig omega square, where omega is the angular speed. Okay, so this is the sum of the translation energy, half mvg square, plus half ig omega square is the energy due to rotation. You could also write this as half io omega square, where io is equal to ig plus m d square, where d is the distance between g and o. Right, that comes from the parallel axis theorem. And finally, this is the last case, is when we have general planar motion. So example would be a rolling disk, rolling or sliding disk. You got to use this formula. Okay, so you see that this formula is essentially the same as the formula for fixed axis. So this is actually the generic formula to find the kinetic energy for a rigid body. Okay, this is a special case when the axis is fixed. Do not use this formula for this case. There are certain conditions under which this is true. Like for a rolling disk, that's true. This formula is true, but it's not generally true. So you're better off always using this formula. And then those formulas you see there are special cases of this particular formula. So for example, pure translation is when there is no rotation. So omega is 0. So you get pure translation. Case of fixed axis, you could use this, or it turns out that V equals r omega, right? Or d omega. So if you put that, shove it in the equation, then you should actually get this formula. Okay, but as I said, this is the more generic case. If you use that, you should never make an error in the energy that you compute. The work done definitions which we saw earlier hold true in this case too. There's no change. Work done by force is, if you have F as a vector and you have the corresponding displacement, then you integrate that uh, force dot dr to get the work done. So that's U. Work done by gravity call that UG, and that is mg delta y. Okay, where mg is acting downwards, delta y is upwards. So you see that gravity is acting downwards, so the force is downwards, delta y is upwards, and that's why the product is negative, because the directions are opposite. And this is nothing new. This is something which I written down earlier in the previous chapter. Then the work done by a spring is US is minus half K S2 square minus S1 square. Okay. No matter if you stretch it or don't stretch the spring, it's always that. And similar to work done by a force, there's a work done by a moment, which only applies for rigid bodies. It doesn't apply for particles, because particles are normally translating, they're not rotating. So that I'll call that UM. It's simply M d theta, and you're going to take the integral appropriately. Okay, so the same principle holds true. Principle of work and energy. Which states that T1 plus the work done. So T1 is the initial kinetic energy plus the work done equals the final kinetic energy. Okay, so there's no change in this formula. This is true for rigid bodies, not particles. You don't see this. Those formulas are the same, all those three. The only change is that the kinetic energy T is now due to rotation. That's the half omega part, omega square part, and then the half mvg part is due to vg square part is due to translation. So the idea is the same, nothing new, except the formulas, particularly that formula is changed. Okay, so this is not going to be terribly hard. It's going to be very similar to chapter 14. Okay, so let's get started on some problems. Okay, the disc, which has a mass of 20 kilograms, is subjected to a couple moment of m equals 2 theta plus 4 Newton meters, where theta is in radians. If it starts from rest, so zero speed, determine its angular velocity when it has made 2 revolutions. So we asked to find angular speed when the disk has made 2 revolutions. One revolution is what? How many radians? 2 pi. So 4 pi radians. Okay, so for a problem like this, the question is, why would you choose to use work done energy methods over F equals ma? So this problem can be solved using F equals ma, right? You have to draw the free body diagram, take the moment about O, that'll give you angular acceleration alpha, and then you can integrate the angular acceleration to get the angular speed when theta is 4 pi. That's one way to do it. The reason why I would use principle of work done instead is because you're asked to find angular speed omega as a function of theta. So whenever you see this thing, well, you're asked to find velocity as a function of displacement or angular speed as a function of theta. I would recommend using principle of work done and conservation of energy as opposed to F equals ma. Okay, so as I said, you can solve it both ways, preferably principle of work done. So let me write that down. So this may be solved moment about O is I alpha, and then integrating using, and then you should integrate omega d theta is alpha, right? So if you do that, you'll solve the problem. However, what we see is if omega is theta is given and omega is asked or unknown, or vice versa. So you could be given omega and told to find theta, then principle of work done and energy is preferred. Okay, so as I said, let's draw the free body diagram just because one is you get points for that. Other thing is, by drawing the free body diagram, you're sure that you don't miss out on any forces. So clearly there is mg. Since it's a pin joint, it will have a vertical force, a horizontal force, and then there is moment m. So this is the FPD. So we're going to use principle of work done and energy, which states that T1 plus U12 equals T2. Okay, let's find these quantities and see if we can solve the problem. So T1 is the initial kinetic energy. So what's the initial kinetic energy? It's 0 because it starts from rest. What's the final kinetic energy? So remember I told you it's half mvg square plus half ig omega square. Okay, where clearly the g is given that, well, it's not given, I think it's given the uniform disk, so g is at the center. So what's half mvg square? What's the velocity of g? Linear velocity. It's 0, right? It's not moving. It's not translating, so that's 0. So we're only left with this part, which is half. The inertia of a disk is mr square divided by 2 times omega square. So this comes out to be mr square omega square divided by 4. Okay, let's find the work done. Now to find the work done, yeah, question. What's the force by free diagram? It's the reaction force. So okay. Okay, so when you find the work done, always ask yourself, what are the forces on the system? There are, well, one, two, three, four forces. Well, one is a moment, but that's also like a force, right? So we need to find the work done due to those forces. So work done due to mg is going to be mg times the displacement of g. Okay? Displacement of g is clearly 0 because it's only spinning, it's not moving. So work done by this force is 0. H and V also act at the same point and they do not lead to motion. So the work done due to all those three forces is 0. Right? The only force which which leads to work done is m. So the only thing left is m d theta, and theta goes from 0 to 4 pi. So given that m is 2 theta plus 4 d theta, so 2 theta squared divided by 2 plus 4 theta 4 pi to 0. So this comes out to be 208.18. So now we have, from the equation, T1 is 0, U12 is 208.18 equals T2 is mass, which is 20 kgs, R, which is 0.3 square, divided by 4 times omega square. And so if you solve this for omega, you get 21.5 radians per second. Okay, so again, you could potentially do this using what you learned in chapter 16, which is one chapter before that, which was in your exam, by using moment about O is I alpha. Maybe you should try to do that at home and see if you get the same answer. Any questions on this? Questions? Okay, let's move on. Let's solve a harder problem. The center O of the thin ring of mass m is given an initial angular velocity of omega 0. If the ring rolls without slipping, determine its angular velocity after it has traveled a distance of s downwards. S is along the plane. Neglect the thickness. Okay, so the question is, the ring has a spin and it has angular speed of omega 0, and because of this, because it's along a ramp and it has a spin, it basically moves downwards under gravity, traveling a distance s. You're going to find the angular speed when it has translated by a distance s, it has moved down, and all through from here to here, it is rolling without slipping. So you've done a lot of such problems previous chapter, right? Rolling without slipping. You could potentially do it that way. You could find the angular acceleration of the ring first. Once you find the angular acceleration, you got to integrate the angular acceleration to find the angular speed when it is traveling distance s. So one way to do it is to use what you learned in the previous chapter. Okay. The other way is actually principle of work and energy. And the reason why I would use that is because, again, if you see in this question, you're told to find the angular velocity when it has traveled a distance s. So find omega when the distance is s. So you're told to find the speed as a function of displacement. So when you see that kind of relation, I would recommend principle of work and energy as opposed to using F equals ma. So let me write that down. You may use F equals ma and m equals r ma plus I alpha to solve the problem. Okay. However, since omega S is given and omega is unknown, we need to find omega as a function of S. So you can use principle of work and energy. Okay, so let me start off with the free body diagram as usual. The only reason I do that is because eventually I'll have to find the work done. I cannot find the work done unless I know the forces acting on the ring. So set up the free body diagram first. mg, there's going to be friction force, there's going to be a normal force, and that's about it. Okay, so principle of work So let me write the principle of work and energy. Okay, which states that T1 plus U12 is T2. Okay, let's try to identify individual things. What's the initial energy? Is it 0? Okay, so what's Vg? What's the velocity of center of mass? Is it at r omega 0, right? Similarly, alpha will be V. So Vg is r omega, just like Ag is r alpha, right? It's derivative. So that's that, plus half the inertia of a ring is m r square, then omega 0 square. So if you simplify this, you should get, I think, mr square omega 0 square. Okay, similarly, we can show that this is the final energy is going to be m r square omega 2 square, right? Use same arguments as T1. So since it's rolling initially, it's going to be rolling in the end, because the entire time it's rolling, you could use the same arguments to write the total energy, new energy, as a function of omega 2. Okay, so the final thing left is we need to find the work done. So for that, we need the forces. And there are three forces here. There's normal force, there's friction force, and then there is gravitational force, mg. We need to find the work done. The work done due to n is going to be n times the displacement of this point in the direction normal to the ramp. What's the work done? It's 0, because this point is not moving in the y direction or this direction. What's the work done by the friction force? Okay, this point is always going to not move, right? It's at rest, instantaneously at rest. So the work done by the friction force is going to be 0. The only force left is mg. Okay. Now mg has two components. There's one component in this direction, there's another component in that direction, the horizontal direction. So this is going to be mg cosine theta. This is going to be, use a different color. mg cosine theta. This is going to be mg sine theta. Right? Because this is theta. Okay, now what we can do is we can try to find the work done due to mg cosine theta and work done due to mg sine theta. So mg cosine theta is acting in the direction normal to the ramp. What's the work done by that force? What's the displacement of g in the 90 degrees direction, this direction? It's going to be 0, right? Because g is not moving in the direction which is 90 degrees to the ramp. So the work done due to this force is 0. The only force which does work is actually mg sine theta. It actually causes the ring to move down a distance of s. So that's the displacement. And since mg is downwards, mg sine theta is downwards, and displacement is downwards, both have the same sign, and so the work done is positive. So given that, we can now shove this in this equation, the principle of work done equation, to get half m r square omega 0 square equal plus mg sine theta times s equals mr square omega g square. So solving for omega g, this should be omega 2. Gives omega 2 is square root omega 0 square plus gs sine theta divided by r square. Okay. So again, angular speed, function of displacement, use principle of work done. Any questions on this? No questions? Looks like I'm slightly ahead of time because I didn't have the quiz question. Hold on.